Right, welcome back, students. Sanibonani abafundi. We're carrying on and we're doing the last piece of series, sequences and series, and we're going to be talking about something called convergent geometric series. So let's take a look at how this looks because it's actually, I think it's quite cool. All right. So what we've got, when we add up a geometric series, one of two things happens. Either it just gets bigger and bigger and bigger, our answer gets bigger and bigger and bigger, as it would be here. If we added up more and more terms of this, it gets bigger without bound. In other words, there's no number that it approaches, it just gets bigger and bigger and bigger, and we say it diverges. Right? Now, if we add up lots and lots of terms of this, all right, let's see what happens. Okay, so we could use our formula here, and we're going to bring up our calculator, and we're going to first work out if we added up 5 terms of this, right? So we're going to put in the various numbers in our formula. We're going to put in A, which is 48, times, now in the brackets we're going to go 1 minus R. Now remember here, R is a quarter. It's 12 divided by 48. It's 0.25. All right, and we're going to raise that to the power of 5 initially. Okay? And then on the bottom, we're going to have 1 minus R. So 1 minus 0.25. Okay, let's see what we get. We get that number there. Now that number there is actually 63,9375. I'm going to write it down in full, 63,9375. Now let's redo that calculation, and we don't have to retype the whole thing. We're going to replay it on our calculator. I'll show you how to do that. We're going to go back and press the left arrow. Now we're back up here, and we're going to change that 5 to a 10. We're going to work out what would happen if we added up 10 terms of this series. Now we get 63, 1, 2, 3, 4 nines and then a 4. Okay, 63,9999. Let's write it down. 63, 99994. Right. It would seem, and I'm hoping you would agree, it would seem that the answer seems to be getting closer and closer to 64. And we say that the series converges to 64. It approaches 64. The more and more terms we add, the closer it gets to 64. Just to connect this with another piece of maths, we have actually what we call an asymptote. And so what happens is the sum gets bigger and bigger and bigger, but it doesn't exceed this line over here. So as we add more and more and more and more terms, this is n and this is Sn, and this is 64 over here. Okay, right. Now let's look at why this happens. Let's understand why. That's something we always want to do in maths. R is a quarter. Okay, so if we look at R being a quarter, that means that this little piece over here, just this tiny little piece over here, when you raise a quarter to a big number, let's just look at what happens there. Let's look at what happens when we raise 1/4 to a reasonably big number. In fact, let's just start off and raise 1/4 to the power of 6. That's not a very big number, okay? It's quite a small answer, all right? It's actually 0.00024. Okay, all right, let's look at what happens when we raise a quarter to, say, the 12. Right, it's a tiny, tiny number. It's heading towards 0. So that piece in the formula goes towards 0. Only if R is if R is a fraction. All right. So, and if that piece goes towards 0, then look at what our formula looks like. It actually looks like this. And this formula here gives us what we call the sum to infinity. No matter how many terms you add up, we're going to get closer and closer to some fixed number. Okay, this only happens, and convergence only happens, when R lies between -1 and 1. Okay, all right. So I'm going to just bring up the calculator again and just show you something here. So if we were to use our formula for this one, this new formula that we've got, A, all right, A was 48, if we remember, over 1 minus 0.25. The number we're going to get here is the limit. It's what the thing approaches. It's 64. Does it ever get there? No, it actually doesn't ever get there. Right? It gets closer and closer and closer. And we'll just show you quickly that although your calculator might say it gets to 64, it actually doesn't. All right. I'm going to just show you what I mean by that. So if we were to use our calculator, and I'm going to go back up to where we were calculating some answers here. All right. Remember over here we had the answer of for 10. Okay. Now let's go and change this to say 17. And our calculator says the answer is 64. It's actually not 64. I'm going to use something on my computer just to show you that it actually is not 64. It's very, very, very close to 64. Let's take a look. Okay, so what I've got here is a very, very powerful online calculating tool. All right, and it's called Wolfram Alpha. It's just a website, wolframalpha.com. And I'm going to type in that same calculation. There it is. Okay, and I'm going to say equals, and let's see what it gives us. Right, and what it tells us is that actually the answer is 63,9999999, and your calculator is not actually powerful enough to give it to that accuracy. Let's add up even more terms. Let's add up, say, 27 terms. All right, and see what this gives us. Okay, and it just gives us more and more nines. Let's add up, in fact, 77 terms. Right, and I'm hoping you're seeing it's getting enormous. All right, it's getting absolutely enormous, this number. But it's not actually, when I say getting enormous, it's not getting enormous at all. It's getting closer and closer to 64, but it actually never gets to 64. But it gets as close to 64 as we like. Okay, right, let's continue then and go back to our workbook here. All right, and so let's just summarize what we've learned so far. What we've learned is convergence only applies to geometric series. It only applies when R, our common ratios between -1 and 1. For all other values, the series will diverge. Okay, now I want to show you something else on the computer. So we're just going to pause briefly and then we'll take a look at that. Okay, so here I've got a little simulation set up in Microsoft Excel, and this just shows us what's happening here. A is 48, R is a quarter, and there are the terms, and in the right-hand column here we've got the answers. Okay, notice it's getting closer and closer. Once again, even Microsoft Excel says, oh, it gets to 64. What I want to show you is that if we change the value of A, let's make the value of A 234. The convergence is not affected. It still converges. It converges to a different number. The only thing that affects convergence is R, okay? And so let's put this back to, say, 2. Let's go to something that would be quite familiar with. Let's go to 2 and 2. Now, our terms are 2, 4, 8, 16. And we can see from the graph here that this is diverging. Notice what's happening to the answers. They're just getting bigger and bigger and bigger. If I make R equal to 1, 1, will it diverge? Yes, it'll still diverge. Notice it diverges a little bit slower. It's only getting up to kind of several billion here now. All right. What if I make R equal to 0, 9? Will it converge or diverge? Guys, it converges when R is between -1 and 1. Let's have a look. It actually converges. All right. And once again, so this one seems to converge to, yeah, it's getting quite close to 20 by the looks of it. All right, and we could work that out with our sum to infinity formula, and we're going to do that just now. Let's go for -1, 1. Will it converge or diverge? It will diverge, because what's going to happen if we look at the terms, they actually get bigger and bigger. They change signs, but they're getting bigger and bigger. And notice that the sum gets bigger and bigger, but it alternates in sign. It's now 3,6, the next one's -2, then +4, then -2,6. And these numbers are getting bigger and bigger, even though they're changing sign. It diverges. All right? What if R is -0,9? Will it converge or diverge? It'll converge, but an interesting thing happens here, all right, is that notice it starts approaching a fixed number. Let's see what it starts looking like. Looks like it's getting pretty close to 1,02, sure, quite an interesting number, all right? It's getting closer and closer to that number, but notice it's approaching it from above and below each time. It's getting closer and closer because the size of these numbers, if we ignore the signs, the size is getting smaller and smaller. So we're either adding or subtracting a smaller and smaller amount. So as we go, it gets closer and closer to an amount. Just to confirm, once again, it doesn't matter what my start term is, it will still converge. If r is between -1 and 1, it'll converge. Okay, right. Hope that little illustration is helpful. We're going to dive back in and we're going to go back to our workbook. So there it is. All right, and we're going to look at the following two examples. Just pause the video very briefly and tell us whether these converge or diverge. Okay, this one over here, r is -3. It will diverge. This one over here, r is 300 divided by 900. r is 1/3. This one will converge. All right, now we're going to talk a little story about a little frog who's trying to jump across a 4-meter field. Right? So the first jump is 2 meters. But now he's tired. So his next jump is only half as big as the previous jump. All right? The next jump, he's even more tired. He only jumps 1/2 meter. All right, and we want to know the total distance he jumps. Is this arithmetic or geometric? It's definitely geometric. What's r? r is 1/2. Each time we're multiplying by 1/2 to get half the distance that he jumped before. Okay, this means that this will converge. Why? When do we get convergence? When r is between 1 and -1. 1/2 is between 1 and -1, so this will definitely converge. So now we can use our formula. Sum to infinity is a over 1 minus r. All right, a is 2. 1 minus 1/2. 1 minus 1/2 is actually 1/2. 2 divided by 1/2. Let's make sure we know how to do that without a calculator. 2 divided by 1/2. All right, and so in fact 2 divided by 1/2 is actually 2 times 2 over 1. It's actually 4. So the question is, does the frog ever reach the pond? Theoretically, no. All right, because it'll get to 3,99999. But for all practical purposes, yes. Okay, now we're going to do another example, an example we think you'll find interesting. And we're talking about 3 friends, Busi, Kwanele, and Tabo. And they want to share a chocolate. Okay, now let's just start off right at the beginning. What fraction do you expect that each friend should get of the chocolate? If there's 3 of them, they should get 1/3 of the chocolate. That's the answer we're kind of expecting to get. But it's quite hard to break a chocolate into bits of 3. So what they do is they break the chocolate into equal bits of 4. That's quite easy because you just break it in half here, all right? And you break it in half here. Now these lines should be exactly straight. And now what is going to happen is that Busi will get a share, Kwanele will get a piece of chocolate, and Tabo will get a piece of chocolate. Now there's a piece of chocolate left. It's hard to break it into 3. So what we do is we break it into 4 again. 4 equal pieces. And Busi will take a piece. Kwanele will take a piece. And Tabo will take a piece. All right? Now there's a piece left. So what do you think we should do? Well, absolutely. Let's just keep on going. Let's just keep on breaking this into 4. Okay? Busi gets a piece. Kwanele gets a piece. Tabo gets a piece. There's a piece left. What do you think we should do? We should break it into 4. Busi gets a piece. Kwanele gets a piece. Tabo gets a piece. Now you might say at this stage, Paul, this is just such a small piece, it doesn't matter anymore. But this is chocolate, eh? This is not just anything, this is chocolate. Nandiga cool. Okay, so let's see what actually happens if we carry on this process forever. Initially Busi gets 1/4 of the chocolate. That's what that piece there is. The next piece she gets is 1/4 of a quarter. The next piece she gets, this piece over here, is actually a quarter of the size of this other piece. So it's actually a quarter times a quarter times a quarter. What sort of sequence are we getting here? We're getting a geometric sequence, all right? And it carries on forever. What is R? What are we multiplying by to get from this term to this term? That's right, R is a quarter. Will it converge? In other words, will Busi's share approach some fixed number, or will it get bigger and bigger and bigger? No, it will converge. It will converge. When do we get convergence? When R is between -1 and 1. So it converges since R is between -1 and 1. And now, what do we know? We can use our formula, and our sum to infinity formula is A over 1 minus R. Right, and so what we get, A is a quarter over 1 minus a quarter. It's actually a quarter over 3 quarters. It's 1 quarter divided by 3 quarters. Now remember how we divide fractions? We get a tip and times, so we get 1 quarter times by 4 over 3. The 4's divide out, and we get an answer of 1/3. Did we expect an answer of 1/3 if there are 3 friends sharing a chocolate? Yes, we did. Does it make sense? It always makes sense. Isibalo ziqaqeka injalo. Right, now in the next lesson we're gonna try some questions. So before you watch the next video, make sure that you've tried them yourself. We look forward to seeing you next time. Have a great day.